And you're going to hear talk about our presentation of Rust. I will tell you what Rust is. It's not oxidized metal as I claimed before. It's a systems programming language that is currently in beta and will be released later this year, to be precise, 15th of May. This is just a very quick intro, right? You should get a glimpse of what Rust is. Do I need the microphone, or can I just speak like that? Yeah? Okay, good. Because it's really difficult to speak with a microphone for some reason. Yeah, because I'm just providing an introduction, a quick intro. If you're interested to learn more and get a more profound idea of what it is, please have a look at this guy, Alex Crichton's talk. You find it on YouTube. It tells you everything and much better than I could possibly do it. Because he is one of the developers of Rust and he's in the core team and great guy. Just my greatest recommendations. Besides that, Rust is a systems programming language. It's on rust-lang.org in case you wanna try it. As you can see here, it's featuring a lot of things like zero-cost abstractions, move semantics, blah 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 blah. But really, this is all. I think I want to focus on what really matters, what sets this programming language apart from all the others that are out there, right? Why do we need another programming language even? Right, Rust is better, so be prepared. But why do we need another programming language? What's the deal here? The current situation is more like this, that we have the very fast languages, they compile down to machine code. So you have lots of control about your memory usage, memory layout, and lots of performance, lots of speed, right? Because you run on the bare metal, basically. But also, currently, this means that it's really, really easy to mess up your program state by, maybe you have a little issue with your pointer arithmetic and you write memory that has already been deallocated, or you read memory that is actually not there anymore, and the list goes on. It's really easy to put a bug, may be very decent, into C or C++ code that can later be exploited and come up as something like Heartbleed, Something. I mean, Heartbleed is very, very common right now when it comes to safety. There are more issues that can be exploited that will, be used at some point against you. Java is kind of hitting a nice middle ground. It's running on a virtual machine. It's still quite fast. And it's really, really hard, actually quite impossible to have memory-related issues. So having null pointer accesses or something like that is not possible in Java, fortunately. And then on the far right, you have fully interpreted languages like Python, Ruby maybe, that have lots of safety. You can't possibly do anything wrong with it in terms of memory issues. But you can't also control your memory, your garbage collected, and they're slow. Rust isn't even on that list because Rust manages to be safe and fast, which is quite an amazing accomplishment. You've basically all the good stuff without the bad stuff combined in one language. And it's kind of hard to believe that this wasn't there before and that this is kind of new today. And if I say Rust is safe and fast, I really mean it that way, like in that particular order. Rust wants to be safe in the first place and fast in the second place. And usually these are excluding each other, as we already learned. But Rust has this special kind of thing going on that makes Rust very safe and fast. So the safety basically comes by using a very sophisticated type system and static analysis that is built into the compiler. It's nothing you have to opt in or need an external tool chain for. It's really just part of the language. This is part of the mentality of the language, and you will feel it everywhere without being overwhelmed by it. It's just built in. It's like, I usually like to compare it with languages, like natural languages, right? If you speak French, then you feel, if you're German at least, you feel like a very open-minded lover kind of guy. If you speak German, you feel more like a soldier. And this kind of mentality that comes with a language, at least in my head, I have this notion of, French and German at least, and English as well. This comes along with Rust. Really, you feel it when you program it. And the safety part of Rust is really just coming in by one major feature, and that's really, if anything is setting the language apart, then it's this one. It's ownership tracking. The safety comes through ownership tracking, and if it sounds simple, then I can tell you that it in fact is simple, because that's really all there is about it. So that's a little tiny program that does the following thing. It creates an integer 5 on the heap. It passes on that integer to a helper, which will then just print that integer. And then the program tries to print the integer one more time. So in theory, you should have 5 in standard output 2 times. But we are in Rust. And you see something like this. That's the first thing you see. It's a compiler error. Use of moved value slot. Then there's some macro stuff that you probably just skip over, and you're more confused than you were before. And then the last line is slot moved here because it has type box U32, which is non-copyable. Okay, so slot moved here, like move semantics, that is ownership. So you have to imagine that this program basically means that I have this box that I put into that I assign to a variable named slot. So currently slot owns the box. And then in the line 3, I don't actually pass it by reference or something. No, I pass ownership to the function called helper. And this really means that if I give you a book, then I can't use that book anymore because you have it. And this is ownership. That's really all that is that you're seeing here. So if I give the book to you, then I can't use the book in line 4 anymore. And the book is the slot here, right? Which is an integer named 5. So if this would all be Rust, like resources can only be owned by a single thing, then it would be really difficult to program anything really, because you want shared ownership at some point. You want to lend out resources and then get them back later. And these lending mechanics are really powerful because they actually allow you to program anything. And this is called borrowing in Rust. So here we go again. Let's see what happens here. In line 2, we create a vector that contains a string that says hi, and then I borrow that. I borrow the first element of the vector, which in turn borrows the vector, right? So ownership tracking is, well, transitive, right? If I borrow something that is a child of a structure or that is deep down in the belly of some container, then I borrow the container as well, right? So ownership tracking is deep. Ownership tracking is something you don't get around. So in fact, by getting the first element out of the vector here and assigning it to a variable, hi, I have a borrow on the vector. So in the 4th line, I try to push something new onto the vector, ho, right? And what is push? Push tries to change the vector, right? But in line 3, as you remember, we've already borrowed something. And the point is that as long as there are readers to some resource, you cannot write that resource, right? So all the borrows first have to go away before I can actually push something onto that vector. So I kind of prepared the inevitable. I kind of prepared you what's going to happen. This program does not compile. Error, cannot borrow v as mutable because it is also borrowed as immutable. And then it shows you line 4, v.push, and then a note, previous borrow of v occurs here. The immutable borrow prevents subsequent moves or mutable borrows of v until the borrow ends. So this compiler is very chatty, obviously. It's like a person sometimes. It really tells you what goes wrong in your program line by line by line, and you ask yourself, what is going on? Honestly, this will be in your head. You will just ask yourself, what did I get into there? This guy on stage who said, try Rust, it changes your world. He was right. It changes your world to a world full of pain. Because the first steps will be painful. That's how I experienced it, but I knew what I wanted from that. Okay, so whatever it says, it basically tells you what I just told you in a few more words. In order to make that work, we just exchange the lines. I'm sorry, this is a bit small. I can't make it bigger either, so actually I can. So that might be a bit better. So in order to fix the program, as you can see, all I did is I switched the line, swapped the lines 3 and 4. So now I write before I borrow, right? So now there is no issue. First, I own the vector here. It's also mutable. And that's another thing we come to in a moment. And then I push on, and then I can borrow, and then this will just be fine. Then another key feature of being safe. Just imagine, for instance, in C or C++, when you have a counter and you want to compare, you have it like if counter equals 5, right? Then most people who are well, C or C++ programmers, they don't say if counter equals or is 5. They say if 5 is counter, right? Because you cannot accidentally assign to a literal value. You know, because in C or C++, every variable by default is mutable. So it's really easy to forget to define something or to declare something as constant. So it's possible that you accidentally write a value that you never intended to write. And that's a huge, well, it's a big cause for certain bugs that you will eventually have to debug, which takes your time. So Rust says everything is immutable by default. Nothing can be changed by default. So in the moment you say something like this, let my value here be 1, and then I say add 1, and then I just try to verify that my value has changed and is now 2. You know, and this function here, it basically takes a mutable borrow to some value, and then I assign, then I just increment it by 1. Right? This is what this program attempts to do, but remember, everything is immutable by default. So what happens here is this. Error, mismatched types. Expected a mutable reference to a 32-bit integer, unsigned integer, and I found a standard borrow. So they differ in mutability. See this? And here's where it happens, add 1. Okay, so that doesn't compile. Let's see what we can do here. And this is a version that looks a bit better. So the line that has changed right now is this add 1, right? So previously it was just, I don't know, is this ampersand? In English, it was just ampersand v, like a borrow of v. And now I explicitly tell it, listen, I want to hand over a mutable borrow to the value that I own, right? And that's what I want here. Let's see if that compiles. Ah, come on, really? Error. Cannot borrow a mutable local variable v as mutable. All right, according to the previous error. So again, everything is immutable by default. So if I want something to be changed later, I need to declare it mutable. And the mutable thing is mut. You know, like it's the opposite of what you do in C or C++. In C, C++, you say const, right? And here you say mut or mute. I don't know, I call it mut all the time. Maybe because I'm German. So, oh wow, the sun really kills everything here. So even more difficult to read. But what you should be able to read here is that it's now let mut v be an integer. And now I have, I own this value in a mutable fashion. I can change it here, which also means that I can hand out mutable borrows to that value, which is just an integer, right? So this is immutability by default in Rust.
Sorry, don't you just tend in your programs to sort of like, oh crap, I need to change it, I'll make it mutable, and then you try to discard it with the safe. How do you always revert back to the safe thread again?
Okay. I'm repeating the question because I'm recording this, and the question was, how do I prevent myself, correct me if I'm wrong, how do I prevent myself to just type let mut all the time everywhere, right? Well, it's more typing. People are lazy. I'm lazy. I'm not doing, I don't like to type a lot. Besides that, you're defeating the purpose. So nobody prevents you from doing that, that's for sure. But actually the compiler, actually the compiler would prevent you from doing that because having mutability everywhere is not what you really want. So you're actually limiting yourself because you can only have one mutable borrow out there at a time. And if you kind of are not discriminating between the cases that you actually want there, you might have difficulty getting your program to compile. I'm just telling. So the safe track is what I've shown. And the compiler reminds you about that whenever you try to compile. I'm just, it's just a little anecdote. By now, and I've been spending like 2 months with Rust by now. By now I have a little borrow checker in my head. I have a little ownership tracker in my head. By now I can kind of anticipate what the compiler would want to say when I write certain things, and that's pretty cool. This is really something that has been evolving in my head, like a little extra brain. And as long as you don't have that, the compiler will just, tell you what's wrong all the time. It's terrible initially, at least it was for me. So, I hope that answered your question. We can have more of a conversation later on. Rust is efficient. Why? Because it has no garbage collection. Rust is a systems programming language. It really is, in the end, boiling down to something that is very, very close to what a C or C++ compiler would do for you. All these abstractions that you've seen with the, mutability borrowing, all these fancy types that I've never shown here, they compile down to, efficient pointer arithmetic, whatever is necessary to make this thing fast. You just allocate stuff using, using primitives that under the hood use malloc and free. Really, there's nothing more to it. No garbage collection needed. This thing is real time. This thing is embeddable. Generics are part of the language. Generics, like C++ templates, but better. Better in the sense that these generics here are much easier to write. They're everywhere as well, so you probably want to know about generics when you learn Rust, because really they are everywhere. Generics are checked at compile time, right? Not at instantiation time. So in C++, when you try to use a template, then the compiler might tell you that all the stuff doesn't work. And you have no idea what the heck is going on, deeply nested types that have like multiple screens of length. And you know how to debug that. You didn't even write that template, right? That is currently which is currently erroring while instantiating it. But in Rust, while you're trying to write a template, the compiler will tell you that it works or not. So if it compiles for you, it can be used by everybody. Concurrency primitive, well, concurrency is, I don't say a big thing, because it's just a standard thing. Whenever you have a programming language and you can't write concurrent programs, you're on the wrong track. So Rust obviously has that. Every primitive you can imagine. Channels, like in Go, for instance, are part of the deal. Threads, thread pools, whatever. I mean, it's part of the language. The cool thing is that thanks to ownership tracking, you will naturally prevent or evade certain issues that you have with, race conditions, for instance, right? Race conditions happen if two threads try to, or if two threads have access to the same resource, and one of them is writing it, at least one of them, and another one is reading it, and the resource is not synchronized, right? That's kind of a race condition, and in Rust, you can't even program that. Such a program wouldn't compile, right? This is Rust. It's quite amazing. I mean, when I said ownership tracking is the main point that sets it apart, then I really mean it, because that is influencing everything else down the line and making it safer, better, and actually easier to program. The last thing is basically interesting for guys who want to write programs for small systems, for Internet of Things devices, like real small hardware. Then you don't want to have a big standard library to carry around. You maybe want to implement your own. So it's a small statically linked runtime that you don't need, You can write your own and really boils down to the hardware. That said, Rust currently runs on all the major platforms, Windows, Linux, OS X, 32, 64, and ARM, and maybe even more that I forgot to mention. But, Rust is everywhere. Not quite as, great as other languages are. Like Go is also everywhere, but I think quite mature. But Rust, is getting there. That's what I'm trying to get at. So one of my last slides, just to highlight the generics part. This is really just to show it to you just once. I'm not getting into details because that would easily take too much time here and might be overwhelming. This just shows how generics in Rust looks like, and what I'm showing off here is the difference between a monomorphic dogfight and a polymorphic dogfight. So the polymorphic function here uses dynamic dispatch to achieve polymorphism, whereas the monomorphic one uses static dispatch. And static dispatch means that this is basically a template function here that gets instantiated depending on what types I actually put in, right? So that's the differences that you have there. When it comes to polymorphism, it's really powerful, and you're totally free to choose what you want. Do you want compile time polymorphism, which is faster because you don't have kind of virtual function calls, or do you want to have runtime polymorphism, which is the polymorphic? Sorry, I actually wrote. Yeah, actually, it doesn't make so much sense. It's dynamic dispatch that the polymorphic one uses. And what else is there? Yeah, a little idea on concurrency. This is an old code example, so if you take it like that, it might not actually compile because I did that talk like 6 weeks ago. That's a long time for Rust because it's moving fast towards the release on May 15th. Oh, actually, that didn't zoom in. And so what you see here is a little example how a standard workflow would look like in Rust. We create 2 channels and 2 threads. One is making work and sending it down the channel. The other one is reading the channel and consuming the work to produce some output. And in the main thread, we're aggregating the results and pushing it to some array. So that's just a tiny example on how threading works in Rust. Because that question might come up, there are no threadlets in Rust right now, no coroutines, nothing that Go has by default. So whenever you do multi-threading in Rust, you have real physical threads there that are kind of heavy compared to Go coroutines or to Go routines in that sense. If I wanted to sum it up, what is Rust? Rust is this new systems programming language that is safe and fast. Right now, it gives you like 90% of the C performance or C++ performance, and there's lots of potential to make this even faster. It compiles down to machine code, so you don't need anything. It statically links most of the stuff in that you need, similar to what Go does. It's really nice to write it, you know. The compiler will be your worst enemy initially, but once you got the hang of it, you will love it, because all of a sudden, it's super difficult to make your program crash. Actually, I never achieved that when I was writing anything, because crashing programs will not compile. It's that easy. There is C integration. I mean, C integration is part of the entire language. I didn't mention that at all, because it doesn't really matter to me, but if you want to link to a C library or even C++ library, you can easily do that in Rust. So you can call into C, and C can call into Rust. Python can call into Rust. Pardon?
So you can't get it to crash.
Yeah, exactly. Unsafe code, right? So there is, if in the moment you interface with unsafe stuff, basically anything that is not Rust, you have to mark this portion of the code as unsafe. But you can put a safe facade outside of it. So if I want to use a C or C++ library from Rust, I would basically write my own interface that is safe on the outside, but inside it has these unsafe portions because they deal with raw pointers and some other memory management that is in some C library that you just have to understand. So if you use unsafe, it basically tells the compiler, hey, trust me, I know what I'm doing. And if you don't know what you're doing, then the program will definitely crash, you know. But that's okay, because you can easily see where your program can crash, either in unsafe portions or in certain areas where you don't actually check the result of an output. And yeah, I would really love to show you more about this, but that's not part of the introduction. There will be another talk of mine that shows you how Rust is used to generate APIs or libraries that allow a Rust program to talk to all the Google services out there. So all of them? Yes, all of them. 78, it's last time I counted. So there you can see all the fanciness that Rust provides and why it's safe and why I can point you at each location in these libraries that has the potential to actually panic your program, which is like crashing your program, but in a controlled fashion. You know, this is really, you want to have a look at Rust code to understand what I mean. You want to try it out to understand what I mean. And you want to be prepared for a steep learning curve. You know, it's not Go. It's not even easy initially, but it's totally worth it. I don't want to write anything else anymore. And it's just like that. I love Rust. Thank you for listening.